Hello everyone, I'm Li Liu from Huazhong University of Science and Technology. I would like to share with you about the experimental verification and the physical description of adsorption dependent squid film damping. As we know, LISA Pathfinder have successfully verified the performance of the inertia sensor and the laser interferometer. The final noise of delta G is much lower than the expectation. It can be found that the lower limit of the noise spectrum is the Brownian noise, which is dependent on the pressure. For the geodesic gravitational wave detection mission Tianqin, the residual acceleration of the gravity reference should be lowered to 10 to minus 15, which is a little bit lower than the requirement of LISA and the result of LISA Pathfinder. So the Brownian noise in Tianqin should be further investigated. The group in the University of Toronto and the group in the University of Washington have independently performed the measurement of Brownian noise using torsion pendulums with different configurations. They pointed out that the mechanisms of Brownian noise in constrained volume is identical with that of the squid film damping. According to the theory of fluctuation and dissipation, we can easily obtain the relation between the thermal noise density and the damping, which is due to the collision of residual gas molecules on the macroscopic objects. In details, there are two types of collisions for the molecules. The one is the complete elastic collision, in which the molecules bounces on the solid surface and only the normal velocity components reversed. The other is the completely inelastic collision, in which the molecules are adsorbed by the solid surface at first and emit from the solid surface then. In this case, the emitting angle follows the cosine angular distribution. Different mechanisms lead to different phenomena. For the rotation of a cuboid test mass, the expressions of the damping coefficients in different cases are quite different. The first line shows the damping expression in infinite volume. The second line shows the actual damping in constant volume. We believe that the real process should contain both the elastic collision and the inelastic collision. So we synthesized these two mechanisms and obtained the modified reaction time tau with a thermal accommodation coefficient sigma introduced. The value of sigma is between 0 and 1. Sigma equals 0 represent all the collisions are completely elastic, and sigma equals 1 represent all the collisions are completely inelastic. This figure shows the damping gap relation with different sigma. It indicates that the sigma can be obtained by measuring the dissipation in invariant gaps. This is the thermal accommodation coefficient measurement scheme and the apparatus. A 60-gram hollow aluminum test mass was suspended by a silica fiber whose Q factor is about 12,000. The twist period of the test mass is roughly 412 seconds. Close to the test mass, two pairs of gold-coated electrodes are mounted on the translational stages. The gaps between the electrodes and the test mass can be adjusted within 2.8 millimeters. In order to avoid the electrostatic effects on the test mass, the stray potentials of the electrodes were measured and compensated precisely. Finally, the damping coefficient or the loss angle of the pendulum can be obtained by measuring the amplitude decay of the twister oscillating. We should notice that the measured loss angle is the total dissipation of the pendulum, which contains both the structural dissipation and the Brownian dissipation. So the measured loss angle when the pressure reaches the ultimate pressure of the chamber should be deducted from them. This figure shows the measured Brownian dissipation at different gaps when the pressure in the chamber is 254 micropascal. This figure also shows the theoretical relation of loss angle against the gap when sigma equals 0 and sigma equals 1 respectively, where the average mass of gas molecule is measured by a residual gas analyzer. From the figure, we can find that the measured dissipation is between the lines of sigma equals 0 and sigma equals 1. This result verified that the real process contains both the elastic collision and the inelastic collisions. The thermal accommodation coefficient can be numerically fitted out as 0.79. We also measured the thermal accommodation coefficient at different pressures. This is the measured loss angle when the pressure is 2.74 MPa. The TAC is fitted out as 0.71. This is the measured loss angle when the pressure is 17.7 MPa. The TAC is fitted out as 0.53. From all the experimental results, we can find that firstly, the TAC is between 0 and 1, which is consistent with our model. Secondly, the TAC is pressure dependent. The higher the pressure, the lower the TAC. In order to explain the pressure dependence of the TAC, we suspect that the elastic collision occurs mainly on the adsorbed molecules on the surface, and the inelastic collision occurs mainly on the solid surface itself. When the pressure increases, the adsorbed molecules on the surface also increases, so the collisions on the solid surface decrease and lead to lower TAC. Based on this hypothesis, we constructed an object function and fitted the measured TAC against the pressure. Here N is the area density of the adsorbed molecules on the solid surface. For our experiment, N is roughly 3.52 times 10 to 15. To summarize, we synthesized the two mechanisms of the action of the molecules on solid surface with TAC introduced, then verified it with a torsion pendulum experiment and observed the pressure dependence of the TAC. Finally, we proposed an interpretation for the pressure dependence of the TAC. However, we should note that the interpretation is too quantitative, and the dependence of other factors such as the material should be further investigated. At last, we still cannot give a clear conclusion about the Brownian noise in Tianqin. Okay, that's my topic. Thanks for your attention.